Hello, good afternoon, good morning, good day, whatever time it is where you are around the world, my friends. Welcome to my microwave and RF design, device design and modeling. Where I'm continuing with this is the third part. This is going to be the third part in the Ferrite circulator design. That is surface mount drop-in devices like strip line and micro strip lines. This is my YouTube channel, and so the first two parts are right here. I urge you all to please go ahead and subscribe to my channel so you get notification as soon as I upload a channel. But we started the first part in the four series ones was the details of the overviewing the theory behind the design and modeling and even application of ferrite circulators and isolators. Then I moved on to, we covered the microstrip ferrite isolator design and modeling using ANSYS HFSS. That's this video here. Now today, uh, basically we're going to cover the third part of this session, and that is basically to go over the design of the strip line ferrite circulators. Okay. And so last time we did cover the macrostrip ones, and the macrostrip ones, the difference is that there's only one magnet on top, and so you still have the Y junction in here. And of course, in that case, we had a substrate and a ground plane. We don't have the bottom magnet. So this is what I'm showing you right here is a strip line circular. Okay. So I'm just showing you how the differences between this and the last sessions where we covered the microstrip one. So again, this is Dr. Mohamed Nezami introducing myself. I'm a freelance RF and microwave circuit designer. Um, you can reach me at this phone number in here. I operate out of Jerash City, Jordan, with many years of experience in the United States. Basically, if you have any RF circuits designs that you need to do, mainly the transceivers, anywhere from DC to 35 gigahertz. I can help you with that. I can do a complete solution design from concept, specifications, system modeling, system analysis, to circuit board, the design and layout, to producing fabrication files, Gerber files, ODB++, whatever, bill of material. You get everything. I work with your BCB house and BCBA, the assembly house as well, and I can even come on your site to help you test the prototype of whatever it is, amplifiers, low noise amplifiers, up converters, down converters, filters, various form of filters, printed and microwave and filters in waveguides or in microstrip, and even cavity filters. Okay, so I know last time we did cover these two types of circulators. The one last time I covered was the design and modeling of microstrip drop-in circulator, ferrite circulator. Today we're going to go over this device here, which is basically the strip line design. And the difference is that this is completely planar where you have a substrate. So you need to install this on a board. You either print the transmission line alongside the edge in here and lay it on top of another BC board, or you make a cutout in the barrier BC board and just drop this in and just jump solder this to the 50 ohm traces, or to the termination in this case, if you're trying to use it as an isolator. Now, the strip line is a little bit different because it has two magnets, and It drops in like this. It's heavier. It's got to have metal on both sides because it's a strip line, meaning there's a ground plane on top and ground plane on the bottom, and the magnets are embedded. Okay, so in a minute you'll see the details of this. So it looks like this, but you still get the strips of metal to the ports in here where you solder to the printed circuit board. Now, next session, I'm going to be designing, showing maybe perhaps one of these ones, either the SMA, the connectorized one or the waveguide one. I may even add another, not 4 videos, but 5 videos where I will cover the waveguide one. So in any case, this was the teardown. I grabbed these from various sources that made a teardown of the of a strip line isolator, and you can see it very clearly here. What it is basically, this in this case, this is a internally terminated circulator, which makes it an isolator. Okay, but what it is basically, you get 2 ferrite cores, and you sandwich in between them a Y junction, metal brass junction. Here it is here. And you just basically connect that to, well, in this case was done on a SMA connector, but in my case, it would be a 50 ohm line, just to solder to a 50 ohm line. Okay, so today let's go back and cover the strip line. And the strip line one is a little bit different. It's more bulky, it's heavier, but it has a little better, more performance and higher power handling. So it's got some other advantages as well. You can check those out. But the general construction, I took this diagram from published papers. So basically what it is really, you still got, just like the microstrip ferrite isolator that we went through in the last videos, which I urge you to watch those before you watch this. Okay, so you still got a Y junction, okay, which is made of a disc with 3 120 degree apart transmission lines, okay, that are suspended in air basically. And then we have 2 cores, 2 ferrite cores in here at a particular diameter. Same thing in here, we have a particular diameter to the disc as well. And then we have 2 metal body that houses this structure in here. And then we got the 2 permanent magnets on top. Now, so we sandwich those together, and that's basically what you would see when you, that's what's inside of here. The only difference is that this is the top side, and there's a bottom side, and around it also we have metal as well, so that you need to common this with the bottom. So you've got to have a housing that connects the whole thing assembly together. I know I got some feedback on the first video designing the microstrip and modeling in HFSS, and somebody mentioned that you know, we put the magnets in here, but these magnets in the model that I have, basically they are really non-model objects. They're just for illustration now, but the effect presence of these is represented in the bias, the magnetic DC bias of the ferrite cores that are here. Okay, the ferrite pieces that are here, the ferrite discs. That's basically, I put a uniform magnetic bias on them, and that's in real life. That's not really what you get, but at least it's a good starting point. It gives you a good verification of the performance. The only difference is that you might get more leakage when you have uniform, where you have an actual B versus H, actual with hysteresis magnetization process. So, but I think there's an example in the there is an example in HFSS, and they do show you the both how to set it up with the, or you can go online and just type HFSS ferrite magnetic biasing using uniform, using non-uniform magnetic field, and it'll show you that. The other feedback that I got is that some people were saying that there are some issues with these magnetic cores, the top and bottom. Some of that material, you need to make sure this material is available commercially. Well, I use the one that is stored in the picked one that was used in stored in the HFSS material library. Now you can go into online and just get whatever magnetic ferrite material that can be offered. I'm not here to. This is just illustration of the design and modeling process. Now, if you can't get this material, you will get something very close to it or similar. And there are many of these materials sold at, like, for instance, you can buy them with disc-shaped, hexagonal shaped at a predetermined diameter sizes. So you can get that online. Okay, so basically, if you look at this vertically, this is what it is in real life. Okay, so you've got basically the two ferrites in here. Sandwiched between them is the strip line in here. It is strip line because you've got two grounds, one on top and one on bottom. Okay, and then you've got two magnets with spacers that are on top and bottom. Okay. And and that's basically what we have here. And so I did this design here. Let me just move this a little bit so you can see the material in here. So if you go, this is basically all the parameters that represents the details of the dimensions of these. I got the radius of the ferrite material, the height of the ferrite, the radius of the disc, the microstrip disc or the strip disc, the length of this line and the width of that line, the strip line, and the conductor thickness, of course. You need that, okay, and the width of that strip line. Okay, so basically it's parameterized, and the reason I do that is because I want to sweep those parameters or use some kind of optimization criteria to get optimal performance. This design here was basically done for the like the microstrip that I did. This was done for 8.5 gigahertz as well, similar to the microstrip case that I covered in the second video of this series. So you can see the return loss, the isolation, and the passband in here with the loss about a gigahertz within 0.5 dB of loss. Okay. Now, similar to that I did before, now you can go into the visualization methods and check out the basically the current density going through the conductor, and you can see that it's basically going from one to this port and nothing going to that port. You could also visualize the E field as well. So you could see that as well. And that's basically like this. So you can see that the field is going in here, going out here, and nothing coming out, or very little coming out here. Okay. So that's what we have. So now let's see now, if you're not happy with the performance, as you know that we did go through some of the equations that the Bosma equations that are intended to do the initial dimensions, which is the radius of the ferrite and disc and the length of these lines and the width of these lines. So let's say that one way to actually optimize this for good performance is you come into the dimensions and you start tweaking those. And that's what I did initially before I ended up with this design here. Is I went in and basically the first thing is looked at what the ferrite disc if I sweep the ferrite disk dimensions, diameter, what is the impact? So you can actually tune it so that you can tune different frequencies, okay, by varying the radius between anywhere between 3.2 millimeters all the way to 3.5 millimeters. And then you could, likewise, you could also do, for instance, once you do that and you pick the right radius, you can do the radius of the conductor. And in this, again, you could go in and sweep the radius of the conductor, the disk conductor, from the value of the Bosma values that you initially started with, and you can again pick whatever one you want, and again that gives you another parameter that you sort of optimized. And then let's see what else you can do. So in any case, you can do the width of the strip line so that you can actually tweak it. Let's see how that looks like. So you can see that the width of the line, what it does, of course, it's not going to change the frequency, but it does change the return loss, which is obvious. And then let's see what else you can sweep the length of the conductor as well. That has to do, of course, that will not change the resonance, but that will definitely change the return loss and the isolation. And so you can see that the resonance has stayed the same, but what happens is you can just get a little bit. I'm not I'm not sweeping a wide range. I just zoomed into a specific range in this case. And then finally, so once you do all of these, you get the final optimized one where you can actually, and this is a quick way of optimizing really. You know, I didn't run the automatic optimizer. This is like tweaked by hand. So this is what it is, and it's pretty good, you can see. Okay. So that's what it is, really, ladies and gentlemen. This is the third video on the ferrite circulator design. Next, what I'm going to do is I'm going to do these two. So basically, I'm going to take the same design that is here and just basically now I don't want it as a surface mount drop-in. So what I'm going to do, I'm going to just encapsulate this in metal and design this basically here, attach some SMA and see what that will do. Okay, so again, let's just review what we have here. Let me just hide everything in here, select all, hide it all, and start just showing you one by one. So we have, the first thing is we've got we've got a Y junction. This is the first thing that you design basically. Okay, so let's just show that. So basically this is, you design this first, okay? And in this case, you realize I still have it in pieces. So you design it by just basically drawing, let's see, let me just do this. So you draw one and then again, you just basically repeat that at 120 degrees. You duplicate that two times more at the 120 degrees. And then next, of course, is you come in and decide on the top and bottom ceramics. I mean the ferrite pieces. So this is what we got. So right now, you can see that, of course, if you really were to model this correctly, you would want to add the glue that glues the two ferrites to the Y, the strip line Y circuit in there. But right now I don't have, I just have basically the line in there, and then there is an air gap in there. Actually, you can see it there. I don't know if you can see, yeah, you can see it here. So there is an air gap in there. So once you do this, now what we do next is we're going to do the top and bottom grounds, okay? So you draw those in. Okay, so that's basically what we have right now. So here is this, of course. And we've got, of course, the top and bottom magnets. Okay, so we've got those two are in there. So this is the structure right now, as you can see. Now, what we do is, of course, we're going to solve the electromagnetic field inside. So we need a vacuum in there. So we're going to put a vacuum in this, in the structure. So now we've got, this is basically air inside. Okay, so, and that's it. And then, of course, we gotta excite the sides. We gotta excite the signals. So we're gonna go get some feeds, slabs. These are 3 slabs. Basically, what we do is we use those to do the feed the signals. These are attached to the strip line to do the signal feeding. Okay, so with that, this device is complete. And so the next thing we do is we just basically excite the ports. We have one excite signal here, second one here, second here. These are wave ports. And then we need to do the magnetization as well for the ferrite. So we excite those two, okay, or both, okay. And then we analyze it. And that's what you get basically after, of course. And then from there, you can optimize until you get the right things in there. So, okay. Well, ladies and gentlemen, I hope you enjoyed this. Please sign up to the channel. So the subscribe to the channel so you get the notification of the next videos coming up. Well, have a great day. This is Dr. Mohamed Nezami. Thank you all. Thank you.